Let's look at these four images. What do they represent? Are you familiar with them? Look at the four images a little bit and give it a thought. Maybe you recognize all of them. You're familiar with all of them. Maybe you've seen three, or maybe just two. Or maybe you recognize one. You're familiar with one, or maybe you can't recognize all of them. It's not critical. But let's look at these images, what they are. Take the first one. This is actually the X-ray diffraction pattern of DNA taken by Rosalind Franklin. This is an image of a molecule, DNA, and this image was used by Watson and Crick to propose the double-stranded structure of the DNA helix, the helical structure. So this is a representation of something inside the body by an image. Let's take this image here. This is actually a very well-known image, very famous, taken in 1895. It is the hand of the wife of Wilhelm Conrad Röntgen. It is befitting that Röntgen received the first Nobel Prize in physics. Röntgen is also the father of biomedical imaging. Think about it. First Nobel Prize in physics awarded to the father of biomedical imaging. Gives you some idea about the importance of biomedical imaging. Later on, X-ray images, the X-ray technique for computed tomography, Cormack and Hounsfield shared the Nobel Prize in 1979. And we will talk about that technique in more details. We'll take this image of blood cells. This is the work of Ruska, who received the Nobel Prize in 1986 for the development of electron microscopy. These are images done by an electron microscope from red blood cells. And last but not least, what you see down here, that's an MRI of the head. We can see the eyeballs here, the retrobulbar fat. This is an MRI of a head. For the development of MRI as an imaging technique, Paul Lauterbur and Sir Peter Mansfield, the latter one a physicist, received the Nobel Prize for Physiology and Medicine in 2003. Together, what these images illustrate is the importance of basic sciences, fundamental sciences, physical sciences, and engineering in developing biomedical imaging technologies that are being used today, so widely used, such as in medical diagnosis and research. I will start here with a definition of biomedical imaging, which is slightly different than what we might consider as imaging. Take, for example, this device here. You are all aware of, we all are pretty familiar with smartphones, we take pictures with it. That is taking a picture. Strictly speaking, it's taking a picture of people, so those are live beings. Someone could call it biomedical imaging, but that's not biomedical imaging that we consider. That's taking pictures. So we'll take here a more general definition of biomedical imaging or bioimaging, and we'll call it it is a localized measurement of a contrast generating biophysical process or effect in the body or organ of a living system. And we will constrain ourselves in this course to techniques that are capable of obtaining this information from a live being, be it an animal, a plant, or a human, but it has to be alive and not extracted. So if we go on, then we have the term here, contrast generating. So what is contrast? What do we understand under the term contrast? We all know what images are. Well, contrast is the ability to distinguish tissue features against noise. In all techniques, imaging techniques or otherwise measurement techniques, we have some level of noise. We need to have enough contrast, that is, features that distinguish different tissues or lesions against normal tissue against the noise background. Then we can say something relevant about what's going on. So essentially, contrast is the difference in signal between the two types of tissues that one wishes to distinguish. Can we see a difference? Then we have contrast. In our classical images, such as the smartphone that you've just seen before, we have excellent contrast, so we can distinguish the features. We can take a picture of you and you're easily able to recognize different people. So in reality, we don't have that much signal-to-noise ratio as we have with cameras. So in reality, for imaging techniques, we have to deal with contrast-to-noise ratios, or the contrast-to-noise has to be considered. So this is the importance of contrast. So now we'll go to what is being measured, and here I want to introduce some useful definitions. Typically, when we take an image, a two-dimensional image, it's an n-time-n matrix of pixels. Where does the term pixel come from? Well, the term pixel is a condensed version of the double word picture element. So people thought this is too long to say and always talk about picture element. At some point one has defined this as pixel. Or we have a 3D image, which is a k times n times m matrix of voxels. And I guess by now you can figure out that what are voxels, and indeed voxel is the short version of volume element. So these are some of the features that we are measuring. Now, what is important for the imaging techniques is the contrast between, be it either voxels for a 3D image or pixels. Typically in this course we're going to restrain ourselves to two-dimensional imaging, so we're going to mainly, if we mean voxels, we really talk about pixels. We won't generalize the techniques to three-dimensional imaging. But what is important is we want to be able to distinguish tissue 1 from tissue 2, say in a neighboring voxel or pixel of the image. Now, in theory, there is nothing that prohibits us from generating matrices with infinite dimensions. We can have n, m, and k for a 3D image with technology. We can make it as large as we want. But stop. There is a problem here. They can't just have it all. So, to rephrase it, is there a free lunch for imaging? And what we see is that no, there isn't. And the general principle is this. If we have here, on this graphic, we have good resolution on the left, poor resolution on the right. So we would like to have really excellent resolution. We can do that. The techniques allow us to do that in principle. So we could have excellent resolution, that is very small voxel dimensions. The price that we pay is that in that end, we typically have poor sensitivity or contrast. If we want to have a lot of sensitivity, then usually we have to pay the price with resolution. So it's this trade-off between resolution on the right side and sensitivity contrast on the other side that are fighting against each other. And depending on what we want to be able to discern, we are trading off one against the other. And it's always this trade-off that stays with us, and that's inherent in all of the imaging techniques. So now comes the question, we've talked about contrast. Now comes the question, what is signal-to-noise ratio, SNR, and the contrast-to-noise ratio? How do they differ? These are two very essential terms with which we characterize the precision or quality of an image and the ability to distinguish tissue features. So now I think we are all in agreement that if you don't have a good signal-to-noise ratio, it's pointless to continue. If you just see noise, then your image has just noise and you cannot see anything. So you need a good signal-to-noise ratio. It is an essential, necessary condition. We'll define here the signal-to-noise ratio, SNR. Let's look at the signal, or the measurement variable. Sometimes it's not the direct signal that we've imaged, but it is a variable that's derived from the image. And we'll consider the standard deviation of its measurement. Standard deviation of the measurement of this signal or the measurement variable means typically it's the variation that's either determined experimentally. Now, how can we do that? The experimental determination. So one way is to repeat the measurement many times and to see how much the same measurement varies over time. This gives us an indication on the variance and therefore on sigma, the standard deviation. In some techniques, we can actually quantitate the standard deviation of the measurement and do a calculation quantitatively for the SNR. So that brings us to a first important definition, that the signal-to-noise ratio is the signal divided by the standard deviation of the noise. So it gives us a idea of the variance. So therefore, this is a means to estimate by which the precision with which the signal is measured. How much does it fluctuate scan to scan? So now, it is in principle possible to have outstanding signal-to-noise ratio, but very poor contrast-to-noise ratio. Can you think of a situation? Well, we'll take the camera here, and let's say we take a picture of you, or of the lecture hall, or of some scene, and we take a very long exposure time. So we collect a lot of, in the CCD device, we collect a lot of photons until we saturate the detector of the camera. Then we have excellent signal-to-noise ratio. We basically have no noise. We have just signal. But when we saturate, we basically are overloading on all aspects the camera, and we just get a white image. So this is an excellent SNR, excellent signal-to-noise ratio, but we won't be able to discern any features with it. So we have no contrast. We can't see if there are people in the picture, if it's a landscape, etc. So while signal-to-noise ratio has to be good, it's a necessary condition. It is not a sufficient condition. So we need to be able to distinguish two signals. We call it, let's say, we call it S1 and S2, and we want to have, for each one of them, good signal-to-noise ratio. Let's assume we have that, but we also need to introduce here the contrast-to-noise ratio, and this is the definition I want to bring in here about. So let's take S1 and S2. Those are two signals from two different tissues or measurement variables. Again, it can be calculated variables from the images, but two features that we are extracting from the tissue. And let's say 1 and 2 are two different tissues. We'll introduce here again the standard deviation, like on the left here for the signal-to-noise ratio. Here, standard deviation. And we'll introduce now for S1 and S2 that the standard deviation of those two tissues, of those two voxels that we want to distinguish, have the same standard deviation. So the sigma is the same, and that the noise is statistically independent. That's true statistically independent measurements. That's what we assume. And so then we define the contrast-to-noise ratio as the difference in the two signals divided by the standard deviation of the noise. So this means, what does this mean? This means we have a signal 1, we have a signal 2, we have a standard deviation. If those two signals differ by not much more than the standard deviation of the noise, we essentially cannot even mathematically discriminate between the two signals S1 and S2. So we won't be able to discriminate between the two tissue types and not detect the lesion or not detect the different tissue types from which. So this is a means to estimate the precision by which we can detect changes in the signal between two tissues.